Okay, so the next reaction we're going to cover regarding alpha chemistry is called alpha alkylation. And it's a pretty straightforward reaction. And what it does is it takes that alpha carbon, meaning the carbon immediately adjacent to some sort of carbonyl, and we add some sort of hydrocarbon to it. So what I mean by that is this alpha position ends up having some sort of sp3 hybridized carbon. All right, in order to do this, we need to first create our enolate, which means we need to apply a base, a relatively strong one, and we need to do an SN2 reaction. And by doing that, this R group over here can essentially be installed coming off of this alpha position. And it's a pretty useful reaction for building up carbon-carbon bonds. So let's take a look at the mechanism here. And the mechanism is pretty straightforward. As you can imagine, if base is required in the first step, then that means that there must be a deprotonation. And it makes sense that we would go after this alpha proton because they're going to be the most acidic. So if we go after this alpha proton, we're going to end up with a conjugate base that is now resonance stabilized. So this is our enolate, where this negative charge can be shared between that carbon and the oxygen in our carbonyl. So we've got this resonance stabilized conjugate base, and then in step 2, all we need to do is react this with some sort of alkyl halide, or really anything with a good leaving group, via an SN2 reaction. So that X could be bromine, it could be chlorine, it could be iodine, or it could even be a tosylate. But the idea is that this carbon with the negative charge, can then attack this R group and kick off our leaving group. And when we do this, we can install a new carbon-carbon bond. All right, there's a couple things to keep track of though, and that is this R group, when we think about it, must be unhindered. If it's a tertiary carbon, you're simply not going to get SN2 chemistry to occur, so it works best if it's a methyl group with a leaving group coming off of it, or a primary carbon with a leaving group. You don't want it to be too bulky or blocked up. All right, so let's take a look at another situation. And this situation is going to be when we have two different types of alpha positions. So let's say we've got this starting material over here, but it's no longer symmetric, right? If we think about it, we've got an alpha position on this side and a second alpha position on this side. So when we think about our alpha protons, we've got alpha protons coming off the left, and we have an alpha proton coming off the right. All right, so now we've got to look at potential products. All right, so if we have a base with a negative charge, there's some sort of probability that it will grab this alpha proton, clamp down, and kick up electrons. All right, and when we do that, we end up with an enolate that looks like this. However, we could also imagine a reaction where we could grab one of these protons, the alpha protons on the other side, and create a different enolate. So let's take a look at these two enolates that we would get out. And then we could ask ourselves, well, which one's going to be the more stable enolate? We've got this one up here that I've highlighted in yellow, and then this one down here that I've highlighted in orange. Well, really what we could argue is the enolate with the more substituted alkene should be the more stable enolate, right? So in this case, this alkene in the yellow box is tetrasubstituted, right? It's got 4 different groups coming off of it. So in this case, this would be the more stable enolate. And we could imagine that in the next step, if we have some sort of alkyl halide, that this negative charge can clamp down, and we could do our SN2 chemistry, where we could get our R group installed off of that side. However, what if there's some sort of probability that this product could end up doing a similar reaction? And we would end up with alkylation on the other side. Whoops, this R group should be over here, not on that right-hand side. All right, so we've got these two theoretical products. Most students, when they see this, they would intuitively say, well, this doesn't make any sense. You just said this is a more stable enolate. Why even bother drawing this one down here? Well, it gets a little bit tricky. One thing I want you to remember is if you're going to a more stable product, that means that you're creating a thermodynamic product. And if you remember back to second term, thermodynamic products can be favored, especially under high temperature conditions. So let's make a note here. So favored at high temp. All right, so we've already covered thermodynamic products, and we said that they're always going to be the result of the more stable pathway, right? Meaning we don't care about activation energy, we just want to get to a product that's more stable. All right, now what I want you to do is to imagine this initial step. So let's imagine this pathway, right? If you're a base and your goal is to grab this proton, that proton's in a pretty crowded nook, right? That proton is coming off of a tertiary carbon. It's somewhat crowded. So if you think about, well, if I'm trying to go after a proton in this crowded little nook right there, should I use a big base or should I use a small base? And in this case, it seems pretty intuitive that we would want to use a small base in order to get into that little crowded spot right here. So we're going to make a second note here that it is best with a small base. All right, now let's imagine what could happen if we have a really, really, really big bulky base, one that, let's say, has some isopropyl groups coming off of it. Well, if you've got isopropyl groups coming off of it, it's going to be incredibly hard to get into this little tiny nook, right? Because that's a tertiary proton. If we come over to this other side, though, if you're a bulky base, those are going to be a lot easier to grab than the protons coming off of the right-hand side, which means that you would likely be making more of this intermediate, that enolate underneath. So this is kind of the interesting duality with a lot of chemistry, is when we think about this, oftentimes we can get a mixture of a thermodynamic product and a kinetic product. And what that means is that it is easier, meaning lower activation energy, to grab less hindered alpha protons. And if we think about this, kinetic products are usually favored at lower temperatures, right? Because we don't want to give it enough energy where it could wiggle its way in and grab this more hindered proton. So it's kind of the opposite of the thermodynamic pathway. And we could say that this is going to be favored at low temp. And like I said before, a lot of this simply depends on the size of your base, that this is favored with bulky bases. All right, so a lot of this is kind of theoretical, right? We've just been using the generic term bulky base, non-bulky base, things like that. All right, so let's take a look at the actual reagents that we would use. So let's give an example down here. And in this example, I'll use the exact same starting materials. And our goal is to favor the formation of our more substituted enolate, resulting in this R group coming off of the more hindered carbon. Like I said up here, this is going to be best with a small base. A small base is going to have an easier time grabbing that more hindered proton. All right, so then the question is, well, what would be an appropriate small base that is also really strong? Because we need to form the enolate, not the enol. And in this case, one of the best small bases we can use is sodium hydride. All right, hydride's very, very small. It does acid-base chemistry, so this would work quite well. And I also said that with thermodynamic products, it works better under high temperatures. In this case, room temp, meaning RT, is really all you need in order to favor this. And then in step 2, we can react this with our alkyl halide. So that works just fine. But the key feature here is that this is a small base. So it's going to favor that more substituted alkene. It's going to be able to fit into that crowded spot more. All right, let's do the other one, where if we have the desire to make the other alkylated product, we're going to have to use a bulky base. And in this case, one of the best bulky bases we can use is LDA. And if you remember, LDA stands for lithium diisopropyl amide. And what this looks like is it's an ion pair, so lithium is the cation, and then you've got a nitrogen with a negative charge as the anion, with 2 isopropyl groups coming off of it. And these isopropyl groups are quite bulky, which means it's going to have a harder time reaching the more hindered proton. All right, so we're going to run this using LDA, and like I said, we can favor the kinetic product at low temperature. So we're going to run this at negative 78 degrees Celsius. And you might be thinking, wow, that's pretty specific. And what this comes from is it's really easy to make a temperature at negative 78 degrees Celsius by combining dry ice, meaning dry ice from the grocery store, with acetone, which is super common in chemistry labs. So this is a bulky base. And then this temperature is basically created by mixing dry ice plus acetone. Some books don't really talk about why they use negative 78. They just throw it at you and say, just use negative 78. It's not that you stick it in a refrigerator set to negative 78. It's just mixing dry ice and acetone. And then in step 2, we're going to mix this with our alkyl halide. Like I said, it needs to be unhindered so we can do SN2 chemistry. And then we can get this kinetic product. So like I said, this top one is going to be our thermodynamic product. And the bottom one's going to be our kinetic product. Sometimes you will get slight mixtures, meaning you might get a major-minor ratio. It really depends on how hindered things are. Sometimes you can get exclusively one versus the other. It just depends on the specific situation. All right, so that's where we're going to stop right now. When we come back, we're going to look at some other alkylation pathways using a bit more complicated syntheses.